Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Reliability Analysis for Buckling Restrained Braced Frame, BRBF, Malavika G Babu M.Tech Student Structural Engineering Department of Civil Engineering Yanis College of Engineering and Technology Kollam, India. Abstract structural demands in high seismic zones require the use of strong lateral framing systems. The structure must have adequate strength and stiffness to resist smaller, frequent earthquakes with limited damage, but must also be able to sustain large inelastic cyclic deformations to economically assure safety and stability during large, infrequent earthquakes. To overcome these problems, a new type of braces called buckling restrained braces, BRBs, was introduced. They are structural steel frame that provide lateral resistance to buckling during seismic activity. This study aims to assess the seismic performance of buckling restrained braced frames, BRBFs, by eigenvalue modal analysis. Equivalent static analysis and time history plots should be created by spectral matching to find out peak response of the building. The reliability index can be calculated by varying building height and plotting the safety margin curves. The modeling and analysis of building is carried out using ETABS software. Keywords: buckling restrained braced frames, BRBFs, eigenvalue modal analysis, ETABS software, reliability index. Introduction: earthquake causes economic losses as well as losses of lives due to the collapse of structures. During strong seismic waves, structural elements like beams and columns are seriously affected. Under moderate to severe earthquakes, conventional lateral load-resisting systems are not effective to overcome these problems. A new type of braces called buckling restrained braces, BRBs, were introduced. They are structural steel frame that provide lateral resistance to buckling during seismic activity. The main components of braces are steel core, bond-preventing layer, and outer casing. The steel core is able to resist axial force acting on bracings. Core is divided into three parts: central yielding part and rigid non-yielding parts at both ends. The bond-preventing layer separates core and casing. It allows free expansion and contraction of core during tension and compression. The casing envelopes the inner parts and restraining the steel core from buckling. In this work, the seismic performance of a 10-story I-shaped BRBF building is evaluated by equivalent static analysis, eigenvalue model analysis. Time history data collected for spectral matching and peak response of building is obtained. Reliability index of structure can be calculated by plotting safety margin curves for different building height. 2. Methodology: data collection, literature review, software study, modeling analysis, results and discussion, conclusions. 3. Modeling: a 10-story I-shaped building is modeled using ETABS software. The materials used are M30 grade concrete and Fe415 grade steel. Height of each story is 3 m. Number of bays in X and Y direction are 7 and 4 respectively. The span of each bay is 3 m. The beam section of size 250 mm x 250 mm and column of size 500 mm x 500 mm is used. Here the provided slab thickness is 120 mm. Fig. 1. Plan and elevation of building. IJERT 10 is 060215 www.ijert.org 512. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Table I. Dead load, is 875, 1987 Part 1, Parapet 2 kN/m Wall load 12 kN/m Floor finish 1 kN/m2 Table 2. Live load, is 875, 1987 Part 2, Residential building 2 kN/m2 Roof 1.5 kN/m2 Table 3. Wind load, is 875, Part 3, Risk factor, K1, 1.0 Topography factor, K2, 1.0 Terrain factor, K3, 1.0 Terrain Category 2 Building Class B Table 4. Seismic load, is 1893:2002, Seismic Zone Factor, Z0.16 Importance Factor, I1 Response Reduction Factor R5 Table V Load Combinations, is 1893, 2002 Part 1, 1.5 dl 0.9 dl plus 1.5 wly 1.5, dl and ll, 1.2, dl and ll and eqx, 1.2, dl and ll and wlx, 1.2, dl and ll and eqx, 1.2, dl and ll and wlx, 1.2, dl and ll and eqy, 1.2, dl and ll and wly, 1.2, dl and ll and wly, 1.5, dl and wlx, 1.5, dl and wlx, 1.5, dl and wly, 0.9, dl plus 1.5 wlx, 0.9, dl plus 1.5 wlx, 0.9, dl plus 1.5 wly, 12, dl and ll and eqy, 1.5. dl and eqx, 1.5, dl and eqx, 1.5, dl and eqy, 1.5, dl and eqy, 0.9, dl plus 1.5 eqx, 0.9, dl plus 1.5 eqx, 0.9, dl plus 1.5 eqy, 1.5, dl and wly, 0.9, dl plus 1.5 eqy. Buckling restrained braced frame on the building should be analyzed. Buckling restrained braced frame Star Seismic is an international manufacturer of buckling restrained braces. The details of braces can be collected from Star Seismic Manual. Star Seismic sections of size 1 INCH2 to 52 INCH2 are available. By selecting Auto Selection option, the software itself select the suitable section for the structure. Here Star BRB of cross-section 26.5 INCH2 is selected. This process is called optimization of BRB. Table 6. BRBF Material Properties Core Material Density 7850 kN/m3 Modulus of Elasticity 2x105 MPa Poisson's Ratio 0.3 Shear Modulus 76903.07 MPa Minimum Yield Stress 262 MPa Minimum Tensile Stress 399.9 MPa Effective Yield Stress 327.5 MPa Effective Tensile Strength 499.87 MPa Table AI. BRBF section detail weight 25.54 knots, depth 406.4 mm, width 304.8 mm, area of yielding core 171 square centimeters, stiffness of elastic segment 4334353.557 kN/m, length of yielding core 4.2672, length of elastic segment 2.2713, linear effective axial stiffness 676,133.98 kN/m. B equivalent static analysis. Here parameters like story displacement, story drift and story shear values of conventional buckling resistance building and BRBF building are compared. For analysis A. Buckling analysis is carried out to predict the maximum load a structure can support prior to instability or collapse. The colored portions indicates regions with buckling load is maximum. The buckling load factors can be obtained from the software. Fig. 2. Column axial load. In conventional method, to avoid buckling we should multiply these buckling load factors as factor of safety to the loads acting on the building and design as per the resultant loads. Instead of this, the provision of using Fig. 3. Story displacement without BRB and with BRB. Maximum value of story displacement for conventional building is 29.57 mm, and for building with BRB the maximum story displacement is 12.02 mm. IJERT 10 is 060215. www.ijert.org 513. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021. See Eigen value modal analysis. Fig. 4. Story drift without BRB and with BRB. Maximum value of story drift for building without is 29.5 mm and maximum value of story drift for building with BRB is 4.92 mm. Fig. 6. Building with BRBF. Fig. 5. Story shear without BRB and with BRB. Maximum story shear for building without BRB is 726.78 knots and maximum story shear for building with BRB 1990 knots. Maximum displacement and story drift get reduced when BRB sections were provided. The base shear increases with increase in weight. Fig. 7. Building without BRBF. For building without BRBF, the modal participating mass ratio becomes 99% at mode 20, and for building with BRBF the modal participating mass ratio becomes 99% at mode 15. Less the number of modes, less will be the distortion of building. Circular frequency 0 means applied load is close to critical buckling load. Target response spectrum according to IS 1893. There are 4 seismic zones in India. Code provide acceleration time graph for each seismic zone based on previous earthquake datas. Time history data from Strong Motion Virtual Data Center. Collect datas of past 12 earthquake occur. Read in India from Strong Motion Virtual Data Center. Spectral matching. In spectral matching, the response spectrum for different seismic zones provided by the code combines with acceleration time graph of various earthquakes collected from Strong Motion Virtual Data Center. IJERT 10 is 060215. www.ijert.org 514. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Fig. 8. Matched Response Spectrum Reliability Index as per IS 1893. Total drift of the building should not exceed 0.004 times the building height. The reliability index is typically used to measure the reliability of the building by using the maximum roof displacement of the building. Margin of safety. The margin of safety of a building is given by the following equation: m equals 1, where equals allowable drift equals maximum roof displacement. Maximum roof displacement for building at different heights are plotted: 30 m24 m18 m12 m6 m Ruarki Uttar Kashi Tari Shillong Panamur Jelal Purgansi Ali Daki Cherapunji Kamalai Shambo Bhuj 0 200 400 600 800 Fig. 9. Roof displacement in x direction, mm, for building with more height displacement is less because lateral load get diminished along the height. The Cherapunji earthquake induce more roof displacement and Shillong earthquake induce least roof displacement. 30 m24 m18 m12 m6 m Uttar Kashi Shillong Jelal per Daki Kamalai Bhuj 0 200 400 600 800 Fig. 10. Roof displacement in y direction, mm, the Cherapunji earthquake induce more roof displacement and Shillong earthquake induce least roof displacement. Figure 11. Safety margin curve for 6m. Safety margin curve for 6m height building is plotted. The standard deviation value is 0.004 and mean value is 0.021 and reliability index value is 5.27 along x direction. For y direction the standard deviation value is 0.003, mean value is 0.021 and reliability index is 8.05. Figure 12. Safety margin curve for 12m building. Safety margin curve for 12m height building is plotted. The standard deviation value is 0.015 and mean value is 0.037 and reliability index value is 2.41 along x direction. For y direction the standard deviation value is 0.035, mean value is 0.026 and reliability index is 0.76. Fig. 13. Safety margin curve for 18m. Safety margin curve for 18m height building is plotted. The standard deviation value is 0.011 and mean value is 0.059 and reliability index value is 5.34 along x direction. For y direction the standard deviation value is 0.086, mean value is 0.016 and reliability index is 0.18. IJERT 10 is 060215 www.ijert.org 515. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Time period, higher circular frequency and higher eigenvalue, so BRBF is more buckling resistant. The reliability index of a structure increases when the probability of failure reduces. Here for 30m building reliability index ranges from 0.11 to 1.7 and for 24m building reliability index ranges from 0.50 to 0.2. For 18M building reliability index varies from 0.18 to 5.34 and for 12M building reliability index is from 0.76 to 2.41. In the case of 6M hay binding the value varies from 5.27 to 8.05. Fig 14. Safety margin curve for 24M height building. Safety margin curve for 18M height building is plotted. The standard deviation value is 0.142 and mean value is 0.029 and reliability index value is 0.20 along x direction. For y direction the standard deviation value is 0.088, mean value is 0.005 and reliability index is 0.05. Fig 15. Safety margin curve for 30M height building. Safety margin curve for 30M height building is plotted. The standard deviation value is 0.043 and mean value is 0.063 and reliability index value is 1.47 along x direction. For y direction the standard deviation value is 0.091, mean value is 0.010 and reliability index is 0.11. Table 8. Develop reliability index for BRBF story height, m. Minimum range maximum range 30 0.111 0.70 24 0.05 0.20 18 0.185 0.34 12 0.76 2.41 65 2.27 8.05 References 1 Kush Agrahishra 1, Keval Patel, Comparative Study on Performance of RC Building with Outrigger System Incorporating Buckling Restrained Bracings International Research Journal of Engineering and Technology Vol. 07 Issue 06 June 2022 YD Kumhar, Study of Buckling Restrained Braces in Steel Frame Building INT Journal of Engineering Research and Applications, Volume 4, Issue 8, August 2014, pages 71-74 3 Arunraji, Vincent Sam Jebadur A.S., Samuel Abraham D., Daniel C., Malavika G. Analytical Investigation of Buckling Restrained Braced Frame Subjected to Nonlinear Static Analysis, Volume 8 Issue 5, June 2019 For Ferdinand, Nyani Ungu and Ji Unchang, Zhao and Chiang, Yang and Wang, Qiaobing and Junja, Research on Application of Buckling Restrained Braces in Strengthening of Concrete Frame Structures. Civil Engineering Journal. 6 344-362. 10.28991/Sej 202003091475. 5 Mohammed Suhaib, Sanjay Rajay and Dr. Sunil Kumar Tengli, 2018. Analysis of Flat Slab Structures with Outriggers, International Journal of Applied Engineering Research Vol 13, No. 7, 2018, pages 72-77 6 Lin, Pao Chun and Takuchi, Toru and Matsui, Ryota, Seismic Performance Evaluation of Single Damped Outrigger System Incorporating Buckling Restrained Braces Earthquake Engineering and Structural Dynamics. 4723432365.10.1002/IC.30722017 Najia, Saida, Dynamic Response of RCC and Composite Structure with BRB Frame Subjected to Seismic and Temperature Load 2248 to 962279. IJERT 2016. 8 Smith, Rob, and Wilford, Michael. 2007, The Damped Outrigger Concept for Tall Buildings. The Structural Design of Tall and Special Buildings. 16 501 517 9 Ayers, J. P. Reagan, and J. Swanson. BRB and FVD Alternatives to Conventional Steel Brace Outriggers. In Proceedings of the TPR Shanghai Conference, pages 691-9. 2014 10 Watanabe, A. Design and Applications of Buckling Restrained Braces International Journal of High-Rise Buildings. 7 215-221. July 2018 11 Ryan A. Kirsting, Larry A. Fonnestock, Walt Ario A. Lopez, Seismic Design of Steel Buckling Restrained Braced Frames NARP Seismic Design Technical Brief No. 11. 12 is, 1893, Part I, 2016, Criteria for Earthquake-Resistant Design of Structures. Bureau of Indian Standard, New Delhi. 13 is, 875, Part 1, 1987 Indian Standard Code of Practice for Design Loads, Other than Earthquake, for Buildings and Structures, Part 1, Dead Loads. 14 is, 875, Part 2, 1987 Indian Standard Code of Practice for Design Loads, Other than Earthquake, for Buildings and Structures, Part 2, Live Loads. V conclusion: by using buckling restrained braced frames, 40% reduction in story displacement and story drift value became negligible when compared with conventional building. The story shear of structure increases due to increase in weight. So BRBF is better than conventional buckling resisting buildings. FEMA 356 recommends 99% mass participation is required to obtain required number of modes in modal analysis. Less the number of modes, less will be the distortion of building. BRBF have less fundamental. IJERT 10 is 060215 www.ijert.org 516. This work is licensed under a Creative Commons Attribution 4.0 International License.